Hello, class. We're going to continue section 3.6, and we're going to focus on modeling using quadratic equations. And what I decided to do is to work on a couple geometric figures, hopefully what I would consider pretty simple, even though this still is reasonably complicated. We're just going to deal with boxes, and actually boxes with square bottoms. And so the first problem is constructing a box where we have a square piece of metal, sheet metal, with regards to the forming of the box. What we're planning on doing is cutting 6 centimeters out of each side, or each corner, excuse me, of the box, and then folding that up to create our box. And the box needs to hold 486 cubic centimeters of volume. And so I'm not the greatest of drawers, so I'm going to steal this picture from the book. And what the idea here is that you can see this is X and this is X. So we have a square, all 4 sides are X. And what we're doing is each corner, we're going to cut out 6 centimeters. And so when we form the box, you can see that we pull these corners up, and so the height is 6 centimeters. So the tricky part is what's left on the bottom, which would be our base, right? Well, if you look at this drawing, you can see that our base is what's left. And how do we calculate that? Well, if this distance is X, the whole side, and we cut out 2 corners of 6 centimeters each, 6 and 6 is 12, right? So what we have left is X minus 12 for the bottom. And so the box configuration would look like this, where we have the length and the width and the height. Now, when you do the calculation for volume, I always look this up, but the volume of the box is the length times the width times the height. And so we have that defined now. That's the hardest part, I think. It's X minus 12 for the length, X minus 12 for the width, and 6 for the height. And we know that must equal 486. So there's a couple ways to solve this. I'll show you one way, and then in the slides you can look at the other way. First thing, regardless of any way, is you want to get rid of this 6. And so let's divide each side by 6 to get started. So when you do that, you have X minus 12 times X minus 12. And if you divide by 6, what do we get? 486. 6 divide gives us a nice number of 81. So this is a square. So you'll see in the slides there's another way to solve it. What I typically do is I just expand it out and then use the quadratic formula if need be. So if you expand this out, you would get x squared minus 12x minus 12x plus 144, right? Equals 81. So if we combine this, you get x squared, and this would be minus 24x. And now if we bring the 81 to the other side, you would get plus 63. And again, because it's a math class, it's set up very strategically, or you could see that 21 times 3 is 63. And 21 plus 3 is 24. So you could actually factor this, and it would be x minus 21. Oops, not 12. Yay, and x minus 3. So we have two possibilities, right? X equals 21 and X equals 3. So are they both true? And how do we check that? Well, the best way to do that again is to go back to our original equation, or I'm sorry, original figure. And you could see that if we plug in 3 for X, what do we end up with for the base? Well, it'd be 3 minus 12, which would be minus 9, which makes no sense. So you could see that the only number that makes any sense is 21. And when you plug that back in there for the base, 21 minus 12 would give us 9. So now we have a real number for, or a positive number for the base, which is important. So to decide what value works and which doesn't, you can't have a negative length for a base. So X equals 21 centimeters. So if you think about what the So what would our box look like, or our piece of sheet metal look like, right? Our piece of sheet metal would be a square, and each side is 21 centimeters. If you're a box manufacturer, nice to know that, especially if you're not making a box at the top. So that's one box application that we're going to talk about. And so that's actually building a box from the ground up. Flat piece of square metal or cardboard if you're making cardboard boxes, etc. The next one that we are going to talk about is this idea of constructing a box. And again, in this one, we're going to do an open top. And we're going to give you what the base is. And so the base, it has a square base, excuse me. So again, both the length and the width are the same dimension. So if the width is X, then the length is X. This problem gets a lot harder when the base isn't square. And we're defining this as 25, volume of 25 cubic feet. And so it expresses the material that you need, which is the flat surface, what we just did in the other problem. Material A, to make such a box, where the length of the square base is X. And so here's what the box would look like. Again, I use these slides because I'm a horrible drawer, but you can see we have two variables. We actually have three variables, but two of them are exactly the same value, right? The width and the length are both X. And what's the height? The height is H. So when we do this analysis, the whiteboard back up here. See, if you looked at this area of the sheet metal in the last problem, that area would be 21 times 21. And so that would be 441 square centimeters is the sheet metal area to build the box that we just did in the last problem. So what we're doing in this one now is that we know that the volume equals 25, and here we're in feet. So it's feet squared, feet cubed, excuse me, cubic feet. And we know that the volume is the length times the width times the height. So the length is X, the width is X, and the height is H. So this would be X squared over H. So we have one equation and two unknowns. So the next thing is we need to find the area equation. And what is the area? Well, let's go back to our box. And walk through how to calculate that. Sorry, but clicking the wrong thing. Okay, back to the box. So the box has a bottom and 4 sides, right? Has no top. So what is the area of the bottom? Well, the area of the bottom is the width times the length. So in that case, it would be x times x. Okay, what would be the area of this side that I'm highlighting with the mouse here? Well, that would be the length, which is x, times the height, which is h. And you can see as you walk around the 4 sides, each one of the area of those 4 sides is exactly the same. It's x times h. So when we generate this equation here, the bottom is x squared. So that's the area of the bottom. And the area of the 4 sides is 4 times x h. That's the 4 sides. And so, well, we have 2 equations and 2 unknowns. And so what we want to do is the problem says how much material is needed if we have the bottom be 5 times 5. So the strategy here is let's get rid of the h, because what are these values? These are x's. So once we get rid of the h, then we could just plug in those x's, the square base, and get the value. So how do we do that? Well, first of all, let's solve for h up here on this equation. So if you want to solve for h, we're going to divide each side by x squared. And so we have h equals 25 divided by x squared. So if we plug this into this equation here, we can get rid of h, and all that is left is x's. So when we do that, we have a equals x squared, and then we have 4x, and we get rid of h by plugging in 25 over x squared. And so we'd have a equals x squared, and this x will cancel with one of these x's in the denominator, and 4 times 25 is 100. So you would have 100 divided by x. So given x is 5 and 5, we plug in a of 5, and you would get 5 squared plus 100 divided by 5. And so that would be 25 plus 20. And so that would be 45. So if the base is by 5, you would have 45 square feet would be the area that you would need for that piece of sheet metal or that cardboard, if it was a cardboard box, to generate this size box with the material that is needed. So that's a couple more examples of quadratic modeling. And that actually ends chapter 3 and ends section 3.6.